So hello everybody, and thank you for joining Adisseo virtual roundtable. 3 years ago we carried out project on small ruminants to determine whether the principle of limiting amino acids, which has been confirmed many years ago in dairy cows, works also on small ruminants. So the strategy was then first determine the efficiency of methionine according to metabolized protein levels, because we know how is the variability in terms of crude protein and MP supplies in the practice, where the crude protein levels is often higher than 18% and the MP supply are often around 120% small ruminants requirements. Second, determine the response of small ruminants to several metabolizable methionine supplies at adequate MP and crude protein levels. And third, confirm the responses at adequate levels of MP and MED according to energy levels, and studied also what happens at the mammary cells level, where we get very interesting and original results. So I will present you in the following slides a summary of the results that we get from this project. The first study was done in collaboration with our colleague Philip Schmidli from AgroParisTech to study the performances and metabolic responses to rumen-protected methionine supplementation in lactating dairy goats fed 2 levels of metabolizable protein diets. Our take-home message is that the lower protein yield responses in goats fed methionine balanced diets result from an underestimated dry matter intake by the INRA 2007 feeding system. As far as we know, there is very limited studies in dairy goats with high level of production supplemented with rumen-protected methionine in dairy goats. Despite the current French feeding system includes recommendation for limiting amino acids in small ruminants that are extrapolated from cows, the real requirements were not demonstrated as done for cows. In Europe, genetic selection is oriented towards higher milk protein content, which is feasible through genetic selection for variants with high casein alpha S1 secretion in goats, and this may affect digestible methionine requirements in these animals. As shown in this graph, for a published experiment study, non-consistent responses to methionine supply were observed on milk production and composition responses. Thus, the objective of the present study, this first study, was to evaluate the performances of high-producing goats to 2 dietary crude protein levels supplemented with rumen-protected methionine to determine if there is any specific methionine requirements. To do that, 16 multifarious alpine goats at 88 day in milk were randomly allocated in individual pen according to their milk casein alpha S1 genotype, body weight, day in milk, milk yield, and milk protein content. They are randomly assigned to low crude protein level 14% and normal crude protein level 16%, without or with 4 grams of rumen-protected methionine as smartamine M to cover around 100% of digestible methionine requirement based on cow recommendation according to INRA 2007 feeding system. The trial was a crossover split plot design for 9 weeks, 2 periods of 4 weeks each, with 1 washout week. Milk and fluid samples were corrected before the morning feeding twice and once per week, respectively. Data were analyzed using the mixed procedure of SAS according to the crossover design. Here are the ingredients, chemical composition, and nutritive values of the experimental diets. This diet corresponds to diets used in some region in Europe. The diets were isoenergy. The difference between 14 and 16% crude protein diets were made by increasing soybean meal and decreasing precipitate pulp in 16% crude protein diet. Digestible methionine was around 1.9% metabolizable protein in control diets and 2.6% in 14 and 16 crude protein diets supplemented with methionine. Digestible lysine was around 7.1% AMP. The results showed that dry matter intake was not affected neither by crude protein level in the diets or methionine supplementation. Crude protein and methionine intakes reflected the experimental design with higher crude protein intake for 16% crude protein diet and higher methionine intake in diets supplemented with methionine. Milk yield was slightly affected by the experimental design, which increased with methionine in 14% crude protein diet, but decreased a little bit in 16% crude protein diet. Milk protein yield was not affected by both crude protein and digestible methionine levels, but milk protein content was higher in goats fed 16% crude protein diet supplemented with methionine. Milk urea increased slightly with methionine, whatever the crude protein content. Even though glucose plasma concentration was not affected by treatments, we observed an increase of beta-hydroxybutyrate in goats supplemented with methionine, which could be explained by a shift of the use of non-esterified fatty acids toward ketone body synthesis, or lower utilization of this beta-hydroxybutyrate. Methionine plasma concentration increased with methionine supplementation. Lysine plasma concentration decreased in 14% crude protein diet and increased in 16% crude protein diets. As conclusion for this first study, increasing crude protein diet and metabolizable protein, PDI, above 14% and 100 grams per kilogram of dry matter, respectively, do not improve the dairy goats' performances. These results showed very weak interaction between casein alpha S1 variant genotype and methionine supplementation. Smartamine provide more digestible methionine in goats as attested by the increase of plasma methionine. In this study, digestible methionine may not have been the first limiting amino acids because the supplies of digestible protein in the intestine exceed the requirement in both 14% crude protein and 16% crude protein diet, which makes not possible to quantify specific digestible methionine requirements. So with that, thank you for your attention, and we'll take any question you may have.
Well, thank you, Lalu. So are you suggesting that the basal diets for goats shall be under 14% crude protein?
Oh, yeah, according to the result that we obtained here, Daniel, that I'm suggesting that we should not, formulate diets higher than 14 or 15% crude protein, and the MP levels, PDI, should be around 100 grams per kilogram dry matter,
Okay. And based on the amino acid profile, do you think that may other amino acids be affecting the milk production or milk protein production in goats?
Oh, according to the results, Daniel, I think that the level of lysine should be higher than 7.0, 7.1 to get a response to methionine. I think that we should put a level of lysine around the requirement established by either around 7.3 according to 2007. Sure.
Okay. Then your one of your conclusions was that there is an overestimation of the dry matter intake of those goats. Why did you conclude that, or this is based on previous information?
Yeah, excellent question, Danielle. Yeah, the reason because when we formulated with the INRA 2007 feeding system, yeah, to get the sorry, yeah, to get the 4 kilogram here of milk production, the model predicts 2.9 kilogram of dry matter intake, and we know that here the dry matter intake is higher than what the model predicts. And when we get these results at the same time, Sylvie Gier from AgroParisTech presented in 3-air meeting here in France. It's a French conference who compared the INRA 2007 system and 2018 system. And at that time, she said that the 2007 underestimated dry matter intake by 20%. So we compare her results, our results, so we get a 20% here underestimation.
Okay. Thank you for clarifying that, Lalu. We do have several other presentations, so I mean, I think we could move forward. And just something that I forgot to tell the audience is that after we are done with all the presentations, we are going to leave open the session for any general questions that may come up after all these posters are being presented. So, I mean, anybody that wants to hang out for a little longer after the last presentation, you can still have a chance to ask questions. So, Lalu, go ahead and with your second presentation then.
Thank you, Daniel. So this second study was done also in collaboration with Philip Schmidli from AgroParisTech to study the performances and plasma energetic parameters in lactating dairy goats fed 3 levels of metabolizable methionine. Our take-home points here are the principle of limiting amino acids may be applied in goats, and the ATARI recommendation for digestible methionine in cows may be used in goats, whatever their genetic variant for casein alpha-1. Despite the current French feeding system includes recommendation for limiting amino acids in small ruminants that are extrapolated from cows, the real requirement were not demonstrated as done for cows. And as I said previously, in Europe, the genetic selection is oriented towards a higher milk protein content, which is feasible through genetic selection for variant with high casein alpha-1 secretion in goats, and this may affect the digestible methionine requirements for these animals. In the previous experiment that I just showed you, we failed to obtain a response of milk protein yield or milk protein content in goats fed high or normal crude protein diets, 16% or 14%, with or without methionine supplementation, which may be attributed to, as I said already, to an underestimated dry matter intake by INRA 2007 feeding system, and consequently exceed the metabolizable protein and digestible methionine requirements in both diets. We cannot exclude that in this diet, digestible lysine may also be co-limiting. Consequently, we aimed to quantify digestible methionine requirement in adequate crude protein diets 14% and determine whether these requirements are affected in goats according to their milk protein secretion as derived by genetic variant of casein alpha-1. 36 multifarious Alpine goats in early lactation, 30 day milk, were blocked in individual pen according to their milk casein alpha-1 genotype, body weight, day milk, milk yield, and milk protein content, and then randomly assigned to their experimental TMR. Goats were fed ad libitum, either a basal control diet, which was unbalanced for digestible methionine, covering around 90% of cows' requirement based on cows' recommendation, or control diet supplemented with methionine through HMBI, Metasmart, pillated in the commercial concentrate at a rate of 1.05 or 1 0.45% as fed to cover 100% or 110% of cow's requirement for digestible methionine, respectively. The trial lasted 12 weeks with 2 weeks of adaptation period to the basal diet. Milk was collected daily before the AM and PM feeding, and fluid samples were collected once a week from week 2 to 12. Data were analyzed with mixed procedure of SAS for repeated measurement with diet and casein genotype as fixed factor. Here are the ingredients, chemical composition, and nutritive values of the experimental diets. Compared to the previous experiment, we added here in this diet the P ingredient to increase the level of lysine. The diets were similar for crude protein, around 14%, starch, around 18%, NDF, around 38%, net energy of lactation, around 1,660 kilocarb per kilogram of dry matter, and metabolizable protein, around 93 gram per kilogram dry matter. Calculated digestible lysine was above the requirement. The diets differ from their digestible methionine from 1.9 from the unbalanced diets to 2.7% of AMP. Dry matter intake was not affected by dietary treatment or casein genotype, and I forget to include the data here. As previously observed, a high genetic variant of casein goats had higher milk protein content and milk protein yield than low genetic variant of casein goats. They also had higher milk fat content. Whatever the casein variant, milk protein content tend to increase with methionine supplementation, especially in treatments covering 100% cow requirements, whereas the treatment covering 110% did not induce further improvement. Contrary to what we observed in the previous study, no change in milk area was observed between dietary treatments. Glucose and beta-hydroxybutyrate were affected neither by casein genotype or by dietary treatments. Methionine supplementation decreased non-esterified fatty acid plasma concentration, suggesting a lower mobilization of lipid in these goats. Insulin was stimulated by methionine supplementation in low genetic variant of casein goats, whereas it was decreased in high genetic variant of casein goats. So, as conclusion, dietary digestible methionine around 2.5% of metabolizable protein is adequate to alpine goats when lysine is not co-limiting. Recommendation for digestible methionine in goats may be similar to cows. The recommendation is adapted to goats with high or low protein yield associated with genetic variants for casein alpha-S1. Thank you for your attention, and please don't hesitate to ask any question you might have.
Thank you, Lalu. Good presentation and very nice done. In this case, compared to the first trial, in the first trial, if I recall, you use smartamine. In this second trial, you use Metasmart. Do you expect any differences in the responses of those goats, goats, excuse me, because of the source of the rumen protected methionine source that you used?
The reason, Daniel, why we used Metasmart HMBI is just for practical reason to incorporate it in the concentrate, just for practical reasons to facilitate the works in the farm, in the experimental farm.
So you don't expect any differences in the responses of
No, the difference could not be due to the source of methionine, smartamine or Metasmart.
Okay. Did you, in this case, did you look into the plasma concentrations of lysine and or methionine?
Yeah, Daniel. We sent all the samples. Yeah, you know that those results are we obtained them recently, and we sent all the samples to the lab, but due to the current situation, the COVID situation, so we get some delay to get the data from the lab. So all the samples were analyzed, and now we are going to analyze the data.
Okay, it would be nice to see what are the concentrations of those amino acids. So that's good. It's good that you have them and that you're trying to.
For sure. And because we are going to publish also the results, so we need this data also.
So one final question, and then we can move forward to the next presentation, Lalu. So you establish that your conclusions in overall throughout these two presentations is that the recommendations in terms of the methionine as percent of the metabolizable protein should be similar to what we are recommending for dairy cows. Would you go with the same for lysine as well?
Good question, Daniel. Yeah, we know that when we increase the level of lysine, the response to the methionine, we get a response to methionine supplementation. So I think that the level of lysine maybe or could be higher than what we have for the cows. So, but for that, we know we have to run some trials to determine the level of lysine. But those trials are focused on methionine.
Yeah.
Methionine, but yeah, maybe the level of lysine could be a little bit higher than those of determined for cows.
So, but at least then, therefore, but at least you have to assure that you have at least a minimum amount of lysine as required for dairy cows. Then.
Yeah, exactly.
Okay. Well, thank you, Lalu. Okay. If you can, when you can move to the your third abstract. So go ahead, please. Thank you.
Thank you, Daniel. So the third experiment was done in collaboration with Sophie Lomoski last year. Sophie working in INRA REN to study first the effect of methionine supplementation at low and adequate net energy supply in lactating dairy goats. So we hypothesized on the interaction between methionine and energy supply due to the high consuming energy in protein synthesis process and milk production. Our take-home message was that methionine balanced diets improved lactating dairy cows' performances without energy interaction. In this study, 48 multiparous meal lactation alpine dairy goats were randomly assigned to 4 groups according to their casein alpha S1 genotype, milk yield and composition parity, and body weight. They received either low or inadequate energy diets with or without methionine supplementation for 6 weeks. All goats received cooked food hay. 10 days before the beginning of the experiment, goats started to receive the low energy or the adequate energy concentrate without methionine. Diets were around 43% forage and 57% concentrate. ISO crude protein around 13.5%, NDF around 40%, and starch around 18%. The adequate energy content in energy concentrate is due to less NDF, more starch as wheat, and fat as hydrogenized oil than in low energy concentrate. Methionine supplementation was done through HMBA as Metasmart that has been pillated in the concentrate at a rate of 0.24%. Dry matter to meet the requirement of 2.5% MP and distributed at the beginning of the experiment. Milk production parameters were analyzed between day 19 and day 32. Blood was sampled on day 28 relative to parturition. A covariance variance analysis was performed using the mixed procedure SAS. The statistical model included the effect of casein alpha as1 genotype, energy, methionine, and the interaction between energy and methionine, all as a fixed effect. Dry matter intake of concentrate was on average 1.52 kilogram of dry matter per day per goat. Forage hay intake per group of 12 goats varied from 13.4 to 14.9 kilogram of dry matter per day. The net energy of lactation density of the two low energy diets were at 1.47 megacal per kilogram of dry matter, and the density of the two adequate energy diets were at 1.54 megacal per kilogram of dry matter. And last, metabolizable protein content for all the diets were at 86 gram per kilogram of dry matter as expected. Milk yield increased significantly with methionine at adequate energy supply. Milk yield tended to increase with net energy supply. Milk protein content increased significantly with methionine supply. And milk protein yield increased significantly in response to methionine and tended to increase with energy supply. Milk fat content tended to increase with methionine supply and increased significantly with energy supply. Milk fat yield increased with methionine supply at adequate level of energy with a tendency of an interaction and increased significantly with energy supply. A plasma concentration of methionine did not vary significantly, probably because methionine uptake by the mammary gland was higher, or the sampling time was not adequate. Methionine as an mTOR amino acid may have increased the mammary gland uptake and utilization of other amino acids. As you can see, the plasma lysine and branched chain amino acid concentration significantly decreased in response to methionine supply. This decrease in plasma lysine concentration also suggests that lysine became co-limiting amino acids with methionine supplementation. Increasing energy supply increased plasma concentration of branched chain amino acids. In conclusion, the principle of limiting amino acids can be applied in high-producing dairy goats as in lactating dairy goats. Since methionine has a positive effect on milk yield and composition in lactating dairy goats, with a greater effect when the level of energy is adequate. The effect on milk yield depends on net energy of lactation. Thank you for your attention. I will take any question you may have.
Thank you, Lalu. I just was looking into your last comments there in terms of the plasma amino acid concentrations and maybe the response to mTOR, some of these amino acids that we do know that they have an impact. I just wonder if energy source, and I don't think you can separate these two because you had the energy source was supplied by both fat and starch, correct? So
correct.
I don't think you can kind of dilucidate if energy source may had an impact on these responses to these goes from the amino acid concentrations, because you both increase both the glucogenic diet or glucogenic energy and the fat energy as well. So, but I think this begs a little a kind of a deeper insight into if you have a differential responses to these amino acids based on the source of energy supplied to these goats. Okay. Well, yeah, no, that's a very nice presentation, Lalu. And I don't know if there are any more questions. We can move to your next presentation. Go ahead, please.
Thank you, Daniel. In the third experiment that we done with Sophie that I just showed you, we collaborated with Mario from INRAT REN, same team than Sophie, to study the effect of methionine at mammary gland cells level. So Mario explored the impact of methionine on gene expression and cell death in the mammary tissues of lactating dairy goats fed low and adequate net energy supplies. And the take-home message from the study is methionine supplementation increases casein gene expression at adequate energy level and reduce cell apoptosis in the mammary tissue of lactating dairy goats. This process may explain the increase of milk protein synthesis. Yeah, we know methionine is an amino acid which has now beneficial effects in dairy cows. Methionine supply increase milk protein yield and content at meal lactation and increase also milk fat yield in dairy cows. A significant increase in milk yield has been observed in dairy cows supplemented with methionine at early lactation. Very few are known about the effect on rumen protected methionine of rumen protected methionine in dairy goats. Amino acid supply effect could depend on the level of energy since milk protein is an energy high cost process. It has been clearly shown that energy levels can impact both cell activity and cell number in the mammary tissues. For example, energy feed restriction clearly reduces the milk yield, and this effect can be associated with both reduction in cell activity and cell number in the mammary tissue. Feed restriction reduced either enzyme activity and milk protein gene expression. Feed restriction is also known to impact proliferation and cell apoptosis balance, and thus impact cell number in dairy cows. Few is known about this effect in dairy goats. The objective of this study was then to understand an underlying cellular mechanism associated with milk yield and composition responses to methionine supplementation at two levels of energy in high producing dairy goats. This is in order to better understand the effect of methionine on cell activity and cell number. From the 48 multiparis alpine dairy goats used in the third experiment that I just presented, we randomly selected 24 goats that have been euthanized after 6 weeks of treatments, and mammary tissues were collected. Briefly for the experimental design. So in the main experiment, we used 48 multiparis mid-lactation alpine dairy goats, where randomly assigned to 4 groups according to their casein alpha S1 genotype, milk yield and composition, parity and body weight. And all of them, they received either low or adequate energy diets, whether without methionine supplementation during 6 weeks. All goats received the hay. 10 days before the beginning of the experiment, goats started to receive the low energy and adequate energy concentrate without methionine, and diets were around 43% forage and 57% concentrate. 47% concentrate, isocrude protein around 13.5, NDF around 40%, starch around 18%. The adequate energy content in energy concentrate is due to less NDF, more starch as weight and fat as hydrogenized oil than in low energy concentrate. Methionine supplementation was done through HMBA, which has been incorporated in the concentrate at rate of 0.24% dry matter to meet the requirement of 2.5% NP, and then distributed at the beginning of the experiment. The net energy of lactation for the low energy diet was at 1.47 megacal per kilogram of dry matter, and the net energy of lactation in the adequate energy diets were at 1.54 megacal per kilogram of dry matter, and the MP level was at a rate of 86 gram per kilogram of dry matter. Total RNA were extracted from the mammary tissues, and milk protein gene expression were analyzed by RT-qPCR. Kappa casein and alpha S1 casein, alpha lactalbumin, and RPS6 KB1 were analyzed as they are related to the regulation of transcription and translation. The rate of cell apoptosis in the mammary tissues was determined after immunodetection of tunnel positive cells. Covariance analysis was performed on the mean of the last week. The statistical model included the effect of casein alpha S1 genotype, energy, methionine, and their interaction, and all of them as a fixed effect. Here are the results from the 24 autoanalyzed goats. Milk yield did not vary according to either methionine supplementation or energy level. However, milk protein yield increased significantly by 9% in response to methionine. Milk fat yield also increased significantly by 10% in response to methionine. Energy has the same positive effect on milk fat yield, with a 10% increase when low energy groups were compared with adequate energy group. Here are the effects of milk protein gene expression in the mammary tissues. Casein alpha S1 and kappa casein gene expression were significantly affected by the treatments, with a significant interaction between energy and methionine. In methionine supplemented goats, energy increased by 3 and 0.9-fold casein alpha S1 and kappa casein level respectively. At adequate energy level, methionine increased significantly by 3.3 and 1-fold casein alpha S1 and kappa casein levels respectively. Alpha lactalbumin gene expression was not affected. The RPS6 KB1 gene related with the regulation and transcription regulation on the transcription and translation, and also in mTOR complex was affected similarly to casein gene expression. In methionine supplemented goats, energy increased by 0.5-fold of RPS6 KB1, and at adequate energy, methionine increased by 0.6-fold RPS6 KB1 transcripts. The upregulation of RPS6 KB1 with methionine has already been observed in mammary epithelial cells cultivated in vitro. Mammary apoptosis rate measured by immunodetection of tunnel positive cells was not affected by energy, but methionine supplementation reduced by 51% apoptosis rate in the mammary tissues. Interestingly, mammary apoptosis rate was correlated with milk yield. So, in conclusion, methionine supply induced an increase in milk protein gene expression at adequate level of energy and reduced cell apoptosis rate in the mammary tissues. This could explain the positive effect of methionine supply on the production of milk protein by the dairy goats. The positive effect of methionine on gene expression level, casein, and also RPS6 KB1 played potentially a role in the increase in milk protein yield found in goats receiving a diet supplemented with methionine. The effect of methionine on milk protein gene expression depends on net energy or lactation. The positive effect of methionine on the rate of cell apoptosis in the mammary tissue could explain the increase in milk protein yield in our study and could also be involved in the beneficial effect of methionine at early lactation in dairy cows. So with that, thank you for your attention, and we'll take any question.
Thank you, Lalu. As we move forward with your presentations, we're getting much deeper, and there is a lot of data to chew on. And again, I'm going to come back to. It looks like there is a direct relationship with amino acids and energy, and in the activity of all these or in the expression of these genes. Yeah. It would be interesting to see if there is an impact of the type of energy that it was supplied to these goats. Did you look for insulin concentration in those plasmas in those goats?
I don't think so, Daniel, because we know that insulin, we have high variation in the insulin measurements. So I think that we did not include that in our protocols.
Okay. I just wonder because it could be an indication. Maybe you could elucidate the source of energy by looking into the increase in insulin concentrations and see if there is an impact on the mTOR activity and the use of those amino acids. But very interesting. Are you aware of if this type of information was done in mammary glands of dairy cows?
I'm not sure, Daniel. I think this is the first time that we show that there's results, especially for the apoptosis, okay, in goats. Because to do that, I think we need to euthanize the animals and have access to the mammary gland tissue. Because when we get the biopsy, for example, for cows, I think that many parameters, including those parameters, will be impacted negatively.
Yeah. Okay. Well, thank you, Lalu, for going through these presentations. Very interesting and very nice data, and a lot of data to chew on again. All right. If we can move to the next presentation, if you want, Lalu.
Well, thank you, Daniel. So last. The same than the slide, the experiment, the project that I just showed you from the third experiment done with Sophie Lemosky. We collaborated with Eric from NRN, also in the same team than Sophie and Mario, to study the effect of methionine in the membrane traffic and secretion of milk components in goats' mammary epithelial cells. So the results, as the results that I just showed you, are very really original results. So we found that diet's energy level regulate membrane traffic in the secretory pathway of mammary epithelial cells. Moreover, the supply of methionine improves the activity of the endoplasmic reticulum and appears to further promote intracellular transport of milk component and ultimately their secretion. It is well known that methionine supplementation increases milk and milk composition in dairy cows. Obviously, we were curious to see whether it would have a similar effect in goats. Moreover, we wondered whether this increase in the secretion of major milk components could be explained by increasing membrane flow in the secretory pathways of mammary epithelial cells in dairy goats. Briefly, both milk protein and lipid are made at the endoplasmic reticulum level, and that in mammary epithelial cells, the release of milk protein by exocytosis and lipids by binding at the plasma membrane are somehow interconnected. So for the experiment, it was the same experiment in Sophie. Briefly, 48 multivariate mid-lactation alpine dairy cows were randomly assigned to 4 groups according to their casein alpha S1 genotype, milk yield, composition, parity, and body weight. They received either a low or inadequate energy diets with or without methionine supplementation during 6 weeks. All goats received the hay. 10 days before the beginning of the experiment, goats started to receive the low energy and adequate energy concentrate without methionine. Diets were 43% forage and 75% concentrate. Methionine supplementation was done through HMBA, okay, as MetaSmart. It has been incorporated in the concentrate at a rate of 0.24% dry matter to meet the requirement of 2.5% AMP and distributed at the beginning of the experiment. The net energy lactation density of the low energy diets were at 1.47 megacal per kilogram of dry matter, and the density of adequate energy diets were at 1.54 megacal per kilogram dry matter, and the metabolizable protein at a rate of 86 gram per kilogram of dry matter. So after six weeks of treatment, 24 goats from the 48 goats were euthanized, and mammary tissues were collected. Proteins were extracted and analyzed by Western blotting using antibodies against specific protein of the subcomponent of the secretory pathway, namely the endoplasmic reticulum, Golgi, and transport vesicles. In addition, we analyzed several regulatory proteins of transport vesicles formation. Western blots signals were quantified and standardized to the signal obtained for cellular actin, and the data were proceed using a various covariance analysis. So as you can see here, Western blot results for a subset of markers. There was substantial individual variation between animals in the amount of some markers. However, if you focus on the calnexin, for example, which is an endoplasmic reticulum marker, you could observe that the signals are somewhat more elevated at adequate energy level with or without methionine. And this is also true for airline 2, which is the marker of endoplasmic reticulum. Here are the results for the full sets of protein we tested. As observed in the previous image, previous slide, we found significant effect of the energy level on the endoplasmic reticulum markers, calnexin and airline 2, with 20% less signal intensity in goats fed the low energy diets. In methionine balanced diets, both markers increased by 20%, as well as on protein disulfide isomerase, PDA, with a 45% increase for this one. On the other hand, AP1, a specific marker of secretory vesicles formation, was at its highest level in goats fed methionine balanced diet at adequate energy supply, and decreased by 25% in goats fed the low energy diets. The Golgi markers are more difficult to interpret, but as a first approximation, the significant higher amount of beta COP found with low energy diets may reflect a decrease in memory transport through and out the Golgi system. So in conclusion, we showed at the cell level our observations are in agreement with a positive effect on methionine on the activity of endoplasmic reticulum. We also found that endoplasmic reticulum activity depends on the net energy of lactation, and the post-Golgi transport is at the highest level at adequate energy level with methionine supplementation. So we can therefore conclude that methionine improves synthesis activity at the endoplasmic reticulum level and has the tendency to further promote interaction intracellular transport of milk components in the secretory pathway and ultimately their secretion into milk. Thank you for your attention, and we'll take any question you may have.
Thank you, Lalu, and what a way to finish up the series of your very high efforts in trying to dilucidate this impact of methionine to goats, which I think is very useful information for all ruminants at the end of the day. We started with this series of roundtables last week, and with the same level of intensity in looking into gene expressions when you're feeding methionine, added methionine to, in that case, if you may recall, during heat stress to dairy cows. Now we are looking where we came to goats, the expression of genes at the mammary gland cell level. This is really very interesting responses, Lalu, and again, I'm going to come back to this question of trying to dilucidate which, if the energy source has a differential impact on the activity of these genes or the expression of these genes, and how this may affect your observation that methionine has an impact on milk fat, as you concluded, is being seen and reported in dairy cows. But I think it is a very nice area of work, and something that we should continue pursuing.
I'm totally agree, Daniel. Working on this source of energy impact will be very interesting. And as you said yesterday, maybe we have to, in the meta-analysis that we presented yesterday, maybe we have to start working that by meta-analysis, by integrating the source of energy and see what the meta-analysis says. But of course, running some trials, studying the source of energy impacts on all these parameters will be very, very interesting and important.
Yeah. So, Lalu, in overall, which other, besides methionine, which other amino acids do you think that is impacting then the responses of goats?
I would say first, from what we learned here, Daniel, first we have to put attention to the prediction of dry matter intake. This is the first thing. Also for the metabolizable protein, which should be around, let's say, not more 100 gram per kilogram of dry matter. So in the two last projects we worked with MP, with PDI levels around 90. Okay, and in addition to the methionine, that will be around the requirement. They said the recommendation, the same one than cows. Lysine will be the second limiting acid for goats. That would be around 7.3% MP, Daniel. But for this project, the histidine, I think histidine level was around 2.1. So that will be interesting also to see if increasing the level of histidine could improve the response to methionine supplementation. So I would say, yeah, first methionine, and lysine should be around 7.3% MP for goats.
Thank you, Dalu. I have one comment. Could you conclude that methionine supplementation, when it's limiting, may affect all metabolic machinery involving milk protein synthesis?
Good question. Very interesting question, Daniel. I think that what we demonstrated with Eric, what we showed in the last presentation with Eric, in addition to the endoplasmic reticulum and Golgi also. So maybe we should see other markers, to integrate other markers in the further experiment, to see how methionine could impact other pathways. Maybe we should include other parameters to determine other biomarkers to determine if it impacts all the machinery biosynthesis.
Okay, we do. It looks like we did see an impact on milk fat synthesis by feeding methionine. Do you think other amino acids may have a similar impact on fat or even in protein synthesis? Let me ask you the question the other way around.
Other amino acids on goats.
What I'm trying to get at, Lalu, is that this impact of there is not a single amino acid that may limit the whole machinery or stop the whole machinery. So that's what I was trying to get at. If it would be the same for goats and than for the lactating dairy cows.
Yeah, maybe Daniel. Maybe it should be the same process, but for that we have to demonstrate that.
Well,
maybe it will be the same.
You have a lot of work to do, Lalu.
Yeah.
If you're going to keep on continuing with small ruminants, I think what I think is really encouraging is to see that these basic principles used in dairy, at the cell level, it can be so far. It looks like we can apply it to dairy goats. Yeah. And probably vice versa. So that's a good thing that we can at least rely on this information and keep on working with that. So
okay. Agree with you, Daniel.
Yeah, the last question I have for you, if there aren't any other questions from the general audience, is you discussed the differences between the INRA models in the old model and the new version. Is the new version of the INRA model is out, or when do you think it's going to come out?
I think you had to ask that question for Daniel Sauvant or Pierre Nozière. But from what I heard, that the software for dairy cows is already available, but for lactating dairy small ruminants, so they are working on. So they said that they will be available soon. So I don't know exactly. Exactly what we get.
Yeah. I know. Working with these models is very, very hard and very complicated. So it's not easy.
They said that the second step will to work on small ruminants, goats and sheep, and then at the end the beef. We're working beef at the last step.
Okay. Well, Lalu, I don't see any more questions coming from the audience. I just want to thank you for all your work. This is a lot of work, a lot of data to digest and to come up to. I hope to see full manuscripts for this so we can read them and ruminate. I mean, it's just giving 10 minutes for each presentation. I know it's not fair. I wasn't fair for any of the presenters. But with this, we conclude the roundtable sessions for ADSA. Thank you, everybody, and stay safe.